When the first humans step onto Mars, and according to current plans this could happen within the next decade, they will take a step that, in the most literal physical sense, may be irreversible. Not because the ship will break, not because something will go wrong in a technical sense, but because the task of returning from Mars is so complex, so dependent on a precise alignment of circumstances, and so demanding in its requirements, that every realistic scenario for early Mars missions contains a genuine possibility that some or all of those who go there may never come home. This is not pessimism, this is physics. Mars is between 54 and 401 million kilometers from Earth, depending on where both planets are in their orbits. The average distance is approximately 225 million kilometers. The journey there on current rocket technology takes between 6 and 9 months one way, and that is only the beginning of the problems. Because you cannot simply fly to Mars and return whenever you want. Orbital mechanics does not work that way. Mars and Earth move along different orbits at different speeds, and they align in a configuration that allows an economical transfer only once, approximately every 26 months. This is called a launch window. If you have arrived on Mars, you must wait for the next window before you can leave for home. This means the minimum surface stay in an optimal scenario is approximately 500 days, nearly a year and a half. A year and a half on a planet with an atmosphere 100 times thinner than Earth's, with a radiation environment several times more intense than on Earth, with temperatures dropping to minus 125 degrees Celsius, with dust storms capable of covering the entire planet for months at a time, with gravity at 38% of Earth's, small enough to cause serious physiological changes, but not small enough to make launch from the surface easy. And after a year and a half on Mars, another 8 months of travel back. A total of more than 3 years away from Earth. 3 years under conditions that slowly and relentlessly change the human body in ways we are only beginning to understand. Tonight, we are going to examine why this is so. What happens to a person on Mars, physically, psychologically, socially? Why return is not simply a technical challenge, but possibly a medical impossibility for those who have stayed long enough. And why the first people on Mars may find themselves, willingly or not, the first Martians, permanently. Before we begin, if you put this on because you need something to carry you through the quiet hours, stay with it. What follows will make you think about courage, and about the price that courage sometimes asks. Let us start with radiation. Because of all the problems associated with a Mars mission, radiation is the most fundamental and the least solved, the one that establishes hard physical limits on what the human body can endure and for how long. Earth is protected from cosmic radiation by 2 shields. The first, the planet's magnetic field, a vast magnetic bubble generated by the liquid metallic core deflecting charged particles from the Sun and from deep space around the planet. The second, the atmosphere, a column of air weighing approximately 10 tons per square meter, absorbing and scattering radiation not deflected by the magnetic field. Together, they reduce the radiation dose at Earth's surface to the level with which biology evolved to cope. Mars has neither shield in sufficient measure. Mars lost its global magnetic field billions of years ago. Its core cooled and ceased generating a protective magnetic field. Some localized magnetic anomalies remain in the crust, but they provide no planetary protection. Mars's atmosphere, primarily carbon dioxide, has a surface pressure of approximately 0.6% of Earth's. This provides roughly the same radiation protection as a thin sheet of paper. The result is a radiation environment on the Martian surface 40 to 50 times more intense than on Earth's surface. An astronaut spending 3 years on Mars would receive a radiation dose significantly exceeding the exposure limits established for professional astronauts. It should be noted that these limits already incorporate an elevated cancer risk. They do not set a safe threshold, but rather an acceptable level of risk for adult volunteers who knowingly accept it. Specific numbers. The Curiosity rover, equipped with a dosimeter, measured radiation on the Martian surface for several years. Results? Approximately 0.64 millisieverts per day on the surface on average. For comparison, the International Space Station delivers approximately 0.5 to 1 millisievert per day, but the ISS is protected by Earth's magnetic field, which deflects the most dangerous portion of the radiation spectrum. On the journey to Mars through open space, the radiation is significantly higher, approximately 1.8 millisieverts per day, as measured by Curiosity during its transit. Let us add it up. 8 months in transit to Mars, approximately 430 millisieverts. A year and a half on the surface, approximately 350 millisieverts. 8 months back, another 430 millisieverts. Total, approximately 1,200 millisieverts, 1.2 sieverts for the entire mission. For reference, the career limit established by NASA for astronauts is 600 millisieverts for women and approximately 800 for men. A single Mars mission would exceed these limits by a factor of 1.5 or more. What does this mean physically? Every sievert of radiation exposure increases the probability of developing cancer by approximately 5.5%, according to standard radiological estimates. 1.2 sieverts means approximately 6.6% additional cancer risk above the normal background risk. This is significant, roughly 1 additional cancer case for every 15 astronauts who complete such a mission. But this is only the averaged estimate. The real danger is uneven. The most dangerous events are solar flare events, when the Sun produces a powerful ejection of charged particles. On Earth and on the ISS, astronauts have some protection. On the way to Mars, essentially none. A powerful X-class flare can deliver a dose of several sieverts in a matter of hours, a dose capable of causing acute radiation sickness. Some historical solar storms were powerful enough to be potentially lethal to unprotected people in open space. We can predict solar flares only a few minutes to hours in advance. This is insufficient to change a spacecraft's course or take any significant protective measures beyond sheltering in the most shielded part of the ship. Sheltering reduces the dose, but not to safe levels during truly powerful events. On the Martian surface, the situation is slightly better than in open space. The Martian soil provides some shielding from one direction. Astronauts could build underground or semi-buried shelters, which would substantially reduce the dose. But the time they spend outside, during surface excursions, scientific expeditions, technical operations, will accumulate. The total dose remains problematic under any realistic scenario for early missions. NASA and other space agencies are working on several approaches to this problem. Active radiation shielding using electromagnetic fields generated by onboard equipment, theoretically possible, but requires enormous energy and has not yet been implemented at the scale needed for a spacecraft. Passive shielding, using water, plastic, or Martian soil as a screen, works but adds mass which is a critical constraint for a rocket. Pharmacological protection. Drugs reducing cellular damage from radiation is under investigation and may reduce risk but cannot eliminate it. None of these solutions is complete. Radiation remains an unsolved, fundamental problem for Mars missions. Not an engineering challenge with a known solution, but a physical constraint requiring either acceptance of risk or a technological breakthrough we do not yet have. Let us talk about gravity. Because Martian gravity, 38% of Earth's, is not merely an inconvenience, it is a fundamental change to the physical environment that shaped human biology across millions of years of evolution. The human body evolved under gravity of 1g, one standard gravitational acceleration of 9.8 meters per second squared. Every organ, every system, every physiological process is calibrated for this gravity. The skeleton is built to handle the loads created by this gravity. The cardiovascular system is calibrated to pump blood against this gravity. The vestibular system is oriented within this gravity. Muscle tone is maintained in response to this gravity. What happens when gravity is sharply reduced, we know relatively well from experience on the International Space Station, though at the ISS it is 0, which is in some ways more extreme than Martian 0.38 g. On the ISS, astronauts lose bone mass at approximately 1 to 1.5% per month, despite intensive exercise. Muscles atrophy. Fluid redistributes toward the head, causing facial swelling and vision problems through increased intracranial pressure. The heart muscle weakens because it does not need to work as hard against reduced gravity. On Mars, these effects will be less pronounced than on the ISS. 0.38 g is still better than 0, but they will not disappear. The question is whether Martian gravity is sufficient for maintaining long-term health. And the honest answer is, we do not know. We have no data on the long-term effects of intermediate levels of gravity on humans. We know what happens at zero gravity. We know what happens at Earth gravity. What happens at 0.38 g over a year and a half or more? This is an area of almost complete ignorance. Some predictions can be made based on physiological models. Bone loss will be less intense than on the ISS, but almost certainly still significant. Calculations suggest approximately 0.5% per month. Over 18 months, that is approximately 9% of bone mass. For comparison, normal age-related losses are approximately 1% per year. An astronaut who has spent a year and a half on Mars may return with a bone age 9 years older than at departure. But this is theory. The reality may be worse, or better. We do not know. What we do know with certainty is that returning to Earth after extended time in reduced gravity is itself a serious physiological challenge. Astronauts returning from the ISS after 6-month missions are often unable to walk without assistance for the first several days. They require weeks or months of rehabilitation to restore normal physical function. Some functions, such as visual acuity impaired by intracranial pressure changes, may not fully recover. An astronaut who has spent 3 years outside Earth gravity, 8 months in weightlessness, a year and a half at 0.38 g, another 8 months in weightlessness, will return to a body no longer adapted to Earth gravity. The readaptation process will be severe, possibly very severe. Possibly, for some individuals, severe enough that complete recovery will be impossible. There is another aspect of the gravity problem that receives less attention. launch from the Martian surface to return home. Mars has 0.38 g and virtually no atmosphere for aerodynamic lift. This means you need a rocket to ascend to Martian orbit before heading home. That rocket must be delivered to Mars in advance. It cannot fly with the crew because it would add too much mass to the ship. It must be ready for use after a year and a half of storage on the surface under Martian conditions. It must reliably function on the first attempt. There will be no second chance. The scenario in which the return rocket fails is one of the most troubling in Mars mission risk analysis. And it is not a purely hypothetical scenario. Throughout the history of spaceflight, there have been numerous cases where rockets failed on first attempts. On Earth, this meant a mission delay rather than the death of the crew. On Mars, it means something entirely different. Now, let us talk about the psychological dimension. Because the physical challenges of a Mars mission, as severe as they are, may be less decisive than the psychological ones. Humans are social animals. We evolved in groups. Our mental health depends on connection, on stimulus, on the sense that we can leave a situation if it becomes unbearable. A Mars mission eliminates all of these in ways that have no precedent in human experience. The closest analogues we have are Antarctic winter-over stations, small groups of people isolated for months in extreme conditions with no possibility of rescue. Psychological research on Antarctic expeditions has documented a cluster of symptoms that appear reliably in long-duration isolated groups. Irritability increasing over time, cognitive decline in certain functions, depression, social friction within the group. What researchers call the third quarter phenomenon, a notable deterioration in mood and function approximately 3/4 of the way through the isolation period as the end comes into sight but still feels impossibly far away. These effects appear consistently even in relatively short Antarctic expeditions, 6 to 12 months. For a Mars mission of 3 or more years, they would almost certainly be more severe. The conditions are different in crucial ways. Antarctic personnel are on their own planet. They breathe real air. They see the sun. They know that if there is a genuine emergency, evacuation is possible in extreme circumstances. Mars offers none of these psychological anchors. A Mars crew would be separated from Earth by a communication delay ranging from 3 to 22 minutes each way, depending on orbital geometry. Real-time conversation with mission control, with families, with anyone on Earth, would be impossible. Every exchange would be a time-delayed message. The intimacy and immediacy of human connection that underlies psychological health would be replaced by asynchronous communication with an 8 to 44-minute round-trip delay. This delay matters more than it might seem. In a crisis, a medical emergency, a technical failure, an acute psychological breakdown, the crew cannot ask Earth for help in real time. They must solve the problem themselves. Mission Control can send advice and support, but the advice arrives after the situation has already developed. The crew is functionally autonomous in every crisis. This creates a burden of responsibility and isolation that has no parallel in any other human mission to date. 6 people, the likely crew size for early Mars missions, confined in a habitat probably not larger than a modest apartment for 3 years. 6 people chosen for competence and psychological stability, but still human, still subject to the full range of human emotion, still capable of developing conflicts, resentments, affections, and alliances that can fracture group cohesion in ways that could compromise mission safety. The research on small group dynamics in extreme isolation is sobering. Groups as small as 6 people develop interpersonal tensions within weeks. Communication breakdowns occur. Hierarchies are challenged. People who appeared psychologically robust in pre-mission selection sometimes deteriorate under the specific combination of stressors present in long-duration isolation. The Antarctic record includes examples of violence, of severe depression, of complete interpersonal breakdowns in groups of highly selected and supposedly psychologically resilient individuals. A Mars crew cannot be evacuated. The group cannot be modified. If one person becomes psychologically unstable, if they pose a threat to themselves or others, the options for managing that situation are extremely limited. There is no psychiatrist to call. There is no authority that can intervene from outside. There are 5 other people and a habitat, and a planet with no way off. Mission planners are aware of these risks. Psychological support systems are being developed, AI-based mental health tools, meditation and mindfulness programs, carefully designed communication protocols, mission architecture intended to give crew members meaningful autonomy and responsibility to maintain their sense of agency. These are real efforts and they matter, but they cannot eliminate the fundamental fact that 3 years of isolation in extreme conditions is beyond anything human beings have been asked to endure in the context of a mission they cannot abandon. Let us talk about what happens to the body at the cellular level, because radiation and gravity are not the only physiological challenges. The human body is a complex adaptive system, and it adapts to conditions in ways that are sometimes helpful and sometimes deeply problematic. Extended spaceflight exposes humans to a combination of stressors that interact with each other in ways we do not fully understand. Take the immune system. Research on astronauts on the ISS has documented measurable changes in immune function during spaceflight, changes that are not fully explained by any single factor. The immune system appears to become dysregulated in space. Latent viruses, including herpes simplex, varicella zoster, and Epstein-Barr virus, reactivate at higher rates in astronauts than in matched controls on Earth. Cytokine profiles shift. Natural killer cell activity changes. The immune system that evolved to protect against pathogens on Earth does not function the same way in space. The mechanism is not completely understood. It likely involves a combination of the stress hormones associated with spaceflight, the altered sleep patterns that occur in low-gravity environments, the disruption of the circadian rhythm by artificial lighting regimes, and possibly direct effects of radiation on immune cells. Whatever the mechanism, the practical implication is concerning. A crew member whose immune system is dysregulated is more vulnerable to infections, to reactivation of dormant viruses, and potentially to conditions like cancer, in which immune surveillance plays a protective role. Add to this the cardiovascular changes. In weightlessness or reduced gravity, the heart does not pump against gravity in the way it evolved to do. It becomes smaller and less efficient. Blood pressure regulation changes. The risk of developing cardiac arrhythmias increases. Some studies of astronauts returning from long-duration spaceflight have shown structural changes in the heart that resolve partially but not completely after return to Earth. And the eyes. Perhaps the most surprising and troubling discovery of recent spaceflight research is the spaceflight-associated neuroocular syndrome, SANS, a collection of structural changes in the eye and optic nerve associated with long-duration spaceflight. Approximately 70% of astronauts who have spent 6 months on the ISS show some degree of SANS. The optic nerve swells, the back of the eyeball flattens. Visual acuity decreases in some affected astronauts. Some of these changes do not fully reverse after return to Earth. The leading hypothesis is that SANS is caused by the cephalad fluid shift, the redistribution of body fluids toward the head that occurs in low gravity, causing increased intracranial pressure that is chronically transmitted to the eye. This is concerning because it implies that even at Martian gravity levels, which are above zero, some degree of fluid redistribution and potentially some degree of SANS might occur. We do not know because we have never studied humans at 0.38 G for extended periods. If significant visual impairment develops during a Mars mission, and based on ISS data this is plausible for a mission of this duration, it could affect an astronaut's ability to perform the complex technical tasks required for surface operations and for piloting the return vehicle. The implications of a crew member with significantly impaired vision during a Mars mission need no elaboration. What makes all of these physiological challenges particularly difficult to manage is that they interact. Radiation damages the immune system. Disrupted immune function affects healing from injuries caused by radiation or any other source. Cardiovascular deconditioning affects the ability to exercise, which affects bone maintenance, which affects fracture risk, which affects the ability to conduct surface operations. SANS affects the ability to work, which affects the ability to manage stress, which affects the immune system. These systems do not function independently. They are coupled, and disruption of one propagates through the others in ways that are difficult to predict and difficult to treat. A Mars crew will have limited medical resources, no hospital, no imaging equipment beyond what can be carried in a habitat, no surgical team, no pharmacist. The medical officer will be an astronaut with additional medical training, not a specialist in any of the specific conditions that might develop. The distance from Earth will make specialist consultation possible, but delayed. The supplies of medications and medical consumables finite. This is the medical reality of a Mars mission. Not catastrophic failure, not the dramatic emergency that gets depicted in films, but a slow accumulation of physiological changes occurring over 3 years in a resource-limited environment far from any possibility of definitive medical care. Changes that are individually manageable but collectively constitute a body that is significantly less healthy at mission end than at mission beginning. A body that will need to perform the physically demanding tasks of return, surviving the transit, re-entry, landing, in this diminished state. Now let us talk about something that the technical and physiological literature discusses less than it perhaps should: the psychological reality of facing a one-way journey. Because there is a real possibility, acknowledged by mission designers but rarely discussed in public, that the first Mars missions will be designed with the expectation that some crew members will not return. Not as a mission objective, not as an official policy, but as an acknowledged statistical reality that some proportion of people who go to Mars on early missions will die there. This is not a new idea in exploration. The expeditions that mapped the poles, that crossed uncharted oceans, that climbed the highest mountains, all of them proceeded with the knowledge that some participants might not return. The difference is that in those historical cases, return was in principle always possible, and the risk of not returning was an acknowledged hazard rather than a design parameter. For Mars, the situation is different in a specific way. The combination of the return rocket requirement, the orbital mechanics constraint, the radiation exposure limit, and the physiological deterioration during the mission creates a scenario where the probability of successful return for all crew members of an early mission is significantly less than 1. Not negligibly less, meaningfully less. Elon Musk has stated publicly that early Mars missions will be dangerous and that participants should be prepared to die. He has framed this as an accepted risk of frontier exploration. This framing is honest in a way that more cautious institutional communications sometimes are not. The danger is real. The risk of not returning is real. People who go to Mars on early missions will know this and will go anyway. What does it mean to knowingly accept a significant probability of never returning to Earth? To leave behind everyone and everything you have known, with the understanding that you may spend the rest of your life, however long or short, on another planet. To board a spacecraft knowing that the statistical expectation is not that you will come back, but that you might come back if everything goes extremely well. This is a psychological reality that has very few parallels in human experience. Not combat. Soldiers face the possibility of death, but typically with the expectation of return if they survive. Not disease. Patients facing terminal illness face death, but not with the element of voluntary choice about the risk. Perhaps the closest parallel is the earliest maritime exploration, expeditions into unknown oceans with no maps and no certainty of return. Those expeditions attracted people for whom the destination was worth the risk of not coming back. The same will be true of Mars. People will go, voluntarily, knowingly, with full understanding of what they are accepting, and some of them may never return. Not because the mission failed in any catastrophic sense, but because the body they will have after 3 years on Mars, radiation altered, gravity adapted, physiologically changed in ways we cannot fully predict, may not be the body that can survive the return journey and the brutal re-entry into Earth's gravity. Let us talk about what Mars offers in return for this risk, because the question of why anyone would accept these terms is not rhetorical. It has real answers that explain why talented and intelligent people are actively training and planning to take exactly this journey. Mars is the most Earth-like planet in the solar system. It has a day approximately 24 hours and 37 minutes long, almost identical to Earth's. It has seasons caused by an axial tilt similar to Earth's. It has polar ice caps. It has ancient river channels and lake beds showing that liquid water once flowed on its surface, possibly for hundreds of millions of years. It has mountains larger than any on Earth. Olympus Mons, at approximately 22 kilometers high, is the tallest volcano in the solar system. It has canyons larger than any on Earth. Valles Marineris, stretching approximately 4,000 kilometers, is roughly the length of the continental United States. More importantly for science, Mars may have had liquid water on its surface for long enough for life to have arisen. The question of whether life ever existed on Mars is arguably the most important question in science after the question of whether the universe contains life beyond Earth in general. And answering it requires not just robotic probes, but humans who can examine geological formations in real time, who can follow unexpected leads, who can apply the full cognitive flexibility of a scientific mind to the problem of understanding what happened on a planet billions of years ago. The human presence on Mars that can answer the question of Martian life, if that life ever existed, is a human presence worth the risk that some of those humans may not return. This is not a cynical calculation. It is the same calculation that drove every major advance in human exploration. The knowledge gained is worth the risk paid. The people who pay the risk understand this and accept it. Mars also offers something more long-term and more existential. It offers redundancy. A single-planet species is by definition vulnerable to extinction through planetary-scale catastrophe, an asteroid impact, a pandemic, a nuclear war, a climate collapse. A species with a permanent presence on 2 planets has an insurance policy against such events. Establishing a self-sustaining human presence on Mars is, in the view of many who think seriously about the long-term future of humanity, one of the most important things our civilization could accomplish. This is the reason that the question of whether the first people on Mars will return is, in some sense, the wrong question. The right question is whether the first people on Mars will build something, a base, a habitat, an infrastructure, a beginning of a presence that makes it easier for the people who follow to survive and eventually to thrive. The first people on Mars may not return, but if they do their job well, they make it more likely that the people who come after them will both arrive and eventually find a way to go home. Let us talk about the specific technical challenge of keeping humans alive on Mars, because the engineering problems of a sustained human presence on another planet are different in kind from anything we have built before. Not harder versions of familiar problems, genuinely new categories of problem that require solutions we do not yet have. Begin with air. The Martian atmosphere is 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, and trace amounts of other gases, including oxygen, at approximately 0.13%. This atmosphere is unbreathable by humans on 2 counts: wrong composition and wrong pressure. Even if you somehow filtered out the CO2 and concentrated the nitrogen and oxygen into breathable ratios, the total pressure of 600 pascals is less than 1% of Earth's sea level pressure of 101,325 pascals. At 600 pascals, even pure oxygen would not sustain human consciousness. You would experience the equivalent of being at roughly 35 kilometers altitude on Earth, above 99% of Earth's atmosphere, well into the death zone. Astronauts on Mars will live and work in pressurized habitats with a controlled atmosphere. This is manageable in principle. We know how to build pressure vessels, and we know how to scrub CO2 from air. The ISS has been doing both for over 20 years. The challenge on Mars is scale and duration. A Mars habitat will need to maintain a pressurized atmosphere for years rather than months, in a more hostile environment, with supplies that cannot be resupplied quickly from Earth, with crew members who have limited ability to make repairs using replacement parts. The failure modes for a habitat life support system on Mars are catastrophic in a way they are not on the ISS. On the ISS, a life support failure can potentially be addressed with crew evacuation to the Soyuz capsule and emergency return to Earth. On Mars, there is no emergency return. A failure of the CO2 scrubbing system means the CO2 concentration in the habitat begins rising. A failure of the oxygen generation system means the oxygen concentration begins falling. Either failure is fatal if not corrected within hours. And correction requires either redundant systems that work or crew members who can repair broken systems using available tools and spare parts. The oxygen situation on Mars has one promising technological development. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, flew on the Perseverance rover and has successfully demonstrated the production of oxygen from Martian atmospheric CO2 using a process called solid oxide electrolysis. MOXIE has produced up to 10 grams of oxygen per hour, far less than the 2,000 grams per hour that a crew of 4 would need for breathing. But it is proof of concept that the technology works. A scaled-up version of MOXIE, deployed before human arrival, could in principle produce enough oxygen to support a crew. But in principle, and reliably enough for life support, are different standards. Water is another critical resource. Humans need approximately 2 to 3 litres of water per day for drinking alone, far more for hygiene, food preparation, medical needs, and any form of agriculture. Carrying all the water needed for a 1,000-day mission from Earth is not feasible. The mass would be prohibitive. Water must come from Mars itself. Mars has water. The evidence is now unambiguous. Ice at the poles, subsurface ice at mid-latitudes, hydrated minerals in rocks and soil, brine potentially present in the subsurface. The Phoenix lander in 2008 directly detected water ice in the Martian soil, just a few centimeters below the surface, at its landing site near the North Polar region. The Curiosity and Perseverance rovers have detected hydrated minerals in Gale crater and Jezero crater, respectively. Radar observations from orbit have detected what may be a subglacial liquid water lake beneath the South Polar ice cap. The question is not whether water exists on Mars, it is whether it can be accessed and extracted reliably enough to support human life. Ice near the surface could potentially be excavated and melted, but early missions will need to verify that their specific landing site has accessible ice before they can commit to depending on it. A mission that lands expecting to extract water and finds that the local soil is drier than expected faces a potentially fatal resource shortfall. Food is the third critical consumable. Carrying enough food from Earth for a 1,000-day mission is even less feasible than carrying water. Dried and packaged food is calorie-dense, but still massive in the quantities required. Growing food on Mars is theoretically possible. The Martian soil contains the basic minerals needed for plant growth, and there is evidence that it may be possible to remove the perchlorates that currently make it toxic to plants through biological remediation. But growing food in a pressurized habitat on Mars at a scale sufficient to make a meaningful contribution to crew nutrition requires agricultural technology and expertise that has never been tested in anything like Martian conditions. The psychological dimension of food also matters. Humans have complex relationships with food that go well beyond caloric needs. The monotony of space food, familiar to anyone who has read accounts of long-duration missions, is a significant contributor to crew morale decline over time. The ability to grow fresh food would have both nutritional and psychological benefits that mission planners consider seriously. But dependence on in-situ food production for survival introduces a vulnerability that is difficult to accept in mission planning. If the crop fails, what then? The most conservative approach to a Mars mission, the approach most likely to get the crew home alive, minimizes dependence on in-situ resource utilization and maximizes the supplies brought from Earth. But this approach maximizes the mass of the mission, which drives up cost and complexity. The approach that makes the mission most feasible economically, maximizing use of Martian resources, maximizes the risk exposure, because each system that must work on Mars is another potential failure point. This tension between safety and feasibility runs through every aspect of Mars mission planning. The safer the mission, the more expensive it is. The more affordable the mission, the riskier it is. There is no design that is simultaneously minimally expensive and minimally risky. The two objectives pull in opposite directions. Let us talk about the specific scenario that mission planners find most troubling. The scenario where everything works as planned and the crew still does not come home. Not catastrophic failure, nominal outcome. In a nominal outcome for an early Mars mission, the crew arrives at Mars after 8 months of transit. They land successfully. They spend 500 days on the surface. They accomplish their scientific objectives. They board the Mars Ascent Vehicle, the pre-positioned rocket that will carry them to Martian orbit, and launch successfully. They rendezvous with the Earth Return Vehicle in orbit. They spend another 8 months in transit back to Earth. They re-enter the atmosphere and land. At this point, they have been away from Earth for approximately 3 years. They have received radiation doses exceeding career limits. They have lost bone mass and muscle mass. Their cardiovascular systems have deconditioned. Their immune systems have been dysregulated for 3 years. Some of them may have developed symptoms of SANS. All of them are physiologically different people than they were at departure, in ways that are difficult to predict in advance. What does re-entry and landing feel like to a body that has spent 3 years at 38% of Earth's gravity and 8 months of that at 0 gravity? The forces involved in a spacecraft re-entry can reach several times Earth's gravitational acceleration, depending on trajectory. An astronaut who has adapted to Martian gravity will experience these forces with a cardiovascular system that has downsized for lower gravitational demand, a musculoskeletal system that has lost mass and density, and a proprioceptive system that has recalibrated its sense of normal to a world that is less than half as heavy as Earth. The ISS experience is instructive here. Astronauts returning from 6-month missions at 0 gravity have been known to lose consciousness briefly during landing due to orthostatic hypotension, the inability of the cardiovascular system to maintain blood pressure when suddenly subjected to gravity after extended weightlessness. 6-month missions. What happens after 3 years is genuinely unknown. We have no data because no human has ever been away from Earth's gravity for 3 years. This is one of the reasons the question of return is not purely technical. Even if the spacecraft works perfectly, even if the radiation doses are within survivable limits, even if the food and water held out and the habitat did not fail, the human beings who step off that spacecraft at the end of the mission will be significantly different from the ones who boarded it 3 years earlier. Whether those changed human beings can survive the physical ordeal of re-entry and landing and readaptation to Earth's gravity is a question that cannot be answered without the data we do not yet have. One possibility that mission designers take seriously is that some crew members, perhaps those with pre-existing vulnerabilities, perhaps those who responded worst to the physiological stressors of the mission, will not be able to survive the return. Their bodies will have adapted to Mars in ways that make the return journey medically impossible. They will be, in a literal biological sense, Martians, adapted to a world that is not Earth in ways that cannot be undone. This is not science fiction speculation. It is a scenario taken seriously enough that it appears in academic literature on long-duration spaceflight medicine. The question of whether extended residence in Martian gravity constitutes a physiological point of no return, a threshold beyond which returning to Earth becomes medically inadvisable or impossible, is one that cannot be answered until humans have actually lived on Mars for extended periods. Let us talk about what it means for a human being to become permanently adapted to another world. Not in the science fiction sense of genetic modification or dramatic transformation. In the quiet, physiological sense of a body that has calibrated itself to conditions different from those of its origin, and that can no longer fully reverse that calibration. We know that human bodies adapt to their environments over time in both reversible and irreversible ways. A person who has lived at high altitude for many years has more red blood cells and more efficient oxygen extraction than someone at sea level. Some of these adaptations reverse quickly when they return to sea level. Others persist much longer. A person who has been sedentary for decades has a cardiovascular system that does not respond to exercise the way a previously athletic person's does. The adaptation to sedentary life has left marks that take years to partially reverse and may never fully reverse. The adaptation to reduced gravity is in some ways analogous. The bone that is lost is not trivially replaced. Bone regrowth is a slow process, and the remodeling takes years even under ideal conditions with adequate nutrition and exercise. The muscle that atrophies must be rebuilt through months of physical therapy. The cardiovascular deconditioning requires sustained aerobic rehabilitation to address. The changes to the eye and optic nerve associated with SANS, if they do not reverse spontaneously, may require surgical intervention or may simply constitute permanent vision impairment. But here is the dimension that the physiological literature tends to underemphasize. The person who has spent 3 years on Mars is not just physiologically different, they are experientially different. They have spent 3 years under alien skies. They have walked on a world where the horizon is closer and the gravity is lighter, and the silence is absolute, and the sky is a dusty orange rather than blue. They have had an experience so far outside the range of normal human life that no one who has not shared it can fully understand it. Astronauts returning from the ISS often describe a period of difficulty readjusting to Earth. Not just physical readaptation, but a sense of dislocation, of the familiar having become strange, of not quite fitting back into the life that was left behind. 6-month missions produce this effect in people who have spent their time in a facility in low Earth orbit, still seeing Earth out the window, still speaking in real time with family and mission control, still recognizably part of the world they came from. 3 years on Mars, truly on Mars, on the surface, separated by a communication delay that makes real-time conversation impossible, surrounded by a world that is not Earth in any detail, would produce a degree of experiential transformation that has no precedent. The people who come back will have been somewhere that no other human has been, and will carry that experience in ways that will not simply dissolve when they step off the spacecraft. Some of them will want to go back, not out of dissatisfaction with Earth, but because Mars will have become, in some sense, home, the place where they accomplished the most significant thing any human has ever done, the place where they developed the deepest bonds with the people who shared the experience, the place that shaped them in ways that Earth no longer can. This is not speculation. It is a pattern documented in Antarctic expeditioners, in submariners, in anyone who has spent extended time in an extreme environment with a small group of people they depended on for survival. The question of whether the first people on Mars will return to Earth may, in the end, be as much psychological as physical. Some will return because they are able and because they want to. Some will return because the mission requires it, and some, perhaps, will choose not to return, even if they physically could. Because Mars, by the time they have spent 3 years there, will have become more real to them than the Earth they left. Because the work will not be finished. Because the place that challenged them and changed them and made them part of something unprecedented will have claims on them that outweigh the pull of the familiar world they came from. Let us talk about what a permanent human presence on Mars would actually look like. Not the distant science fiction version of a terraformed planet with cities, but the near-term, realistic version of what the first sustained presence might be. The first habitat would be small. Inflatable modules or rigid prefabricated structures, most likely a combination, providing perhaps 100 to 500 cubic meters of pressurized living space for a crew of 4 to 6. This is approximately the size of a modest apartment or a large house. In this space, the crew would sleep, eat, work, exercise, conduct medical care, manage mission systems, and spend every non-working hour they are not in spacesuits. The habitat would need to provide radiation shielding. The most effective approaches involve burying the habitat under Martian soil, regolith, using robotic equipment deployed before crew arrival. Several meters of regolith provide significant gamma-ray and cosmic ray protection. It does not fully solve the radiation problem, but it reduces it to a manageable level for the hours the crew spends inside. The combination of habitat time and EVA time would need to be carefully managed to keep total dose within acceptable limits. Power would come from nuclear fission reactors, the most reliable and energy-dense option for a Mars surface operation that cannot depend on sunlight during dust storm season when solar panels may be covered or ineffective for months at a time. NASA's KiloPower project has developed a small fission reactor design specifically for planetary surface applications. A small array of these reactors could power a Mars habitat and its associated systems continuously, regardless of atmospheric conditions. Water extraction would begin before crew arrival, using robotic systems drilling into the regolith to access subsurface ice, and heating it to extract water vapor, which is then condensed. Oxygen would be produced from atmospheric CO2 using MOXIE-derived technology. These in-situ resource utilization systems would need to demonstrate reliable operation for months before crew arrival, because the crew's survival will depend on their continued function. Communication with Earth would be through a combination of direct-to-Earth radio and relay satellites positioned in Martian orbit. The communication delay, 3 to 22 minutes each way, means that all mission operations that might require real-time decisions must be managed autonomously by the crew. This is a profound departure from current spaceflight operations, in which mission control provides near-continuous support and can intervene in real time. A Mars crew is operationally independent in a way that no crew has been before. The scientific program of the first human Mars mission would be extraordinary, even by the standards of what robotic missions have already accomplished. Humans can do geology in hours that rovers take months to accomplish, selecting samples, following unexpected features, adapting their investigation in real time in response to what they find. The history of geological exploration on Earth demonstrates that the most significant discoveries are often made not by following a pre-planned program, but by experienced observers responding to something unexpected in the field. Mars's history of water, and the possibility that life existed there when water was abundant, would be the central scientific focus. The regions most likely to have preserved evidence of ancient Martian life are the ancient lake and river beds, the hydrothermal deposits, and potentially the subsurface where liquid water may still exist. A human geologist in these locations, with the full cognitive flexibility of a scientific mind and the ability to interact with the environment directly, would transform what is currently possible with robotic probes. This scientific potential is part of why the question of return is complex. If the mission is producing science of unprecedented importance, if crew members are actively making discoveries that answer questions humanity has asked for centuries, the calculation about whether to remain or to return is not simple. The science does not end because the optimal departure window has opened. The discoveries do not pause because it is time to go home. Let us talk about what the first generation of Martian settlers, if the word settler is eventually appropriate, might look like as a human community. Because the long-term vision for Mars involves not a series of short visits, but a sustained presence that eventually becomes self-supporting and then self-governing. A self-supporting Mars colony, one that does not depend on regular resupply from Earth for its survival, requires a population large enough to maintain the technical knowledge and practical skills needed for all the systems that sustain life. The estimates for minimum viable population for a self-sustaining Mars settlement range widely, from a few hundred to several thousand people, depending on assumptions about the level of technological sophistication, the degree of automation, and the diversity of skills required. The people who build this community will not be choosing between Earth and Mars in the way that early mission crew members choose. They will be choosing Mars as their home in a more permanent sense, knowing that return to Earth is possible in principle, but increasingly impractical as the community develops its own economic and social life. Their children, if they are born on Mars, which raises its own profound biological questions about development in reduced gravity, will be Martians in a sense that the first arrivals are not. The planet will be all they know. This generational transition from a scientific outpost staffed by Earth-born volunteers on temporary assignment to a permanent community with its own children and its own culture and its own relationship to the planet, is where the question of return becomes permanently answered. Not for individuals who must decide whether to leave, but for a community that has decided, collectively and irreversibly, that Mars is home. The first people who do not return to Earth may be making a choice. The people who follow them, their children, their grandchildren, will not be making a choice. They will simply be Martians, born on Mars, adapted to Mars, unable without significant medical support to survive Earth's gravity, even if they wanted to. The question of return will have resolved itself not through any single decision, but through the accumulation of generations of commitment to a world that is not Earth. This is perhaps the most profound implication of the question we are examining. The first humans on Mars who do not return are not failures. They are not victims of a mission that went wrong. They may be the founders of something, a community, a culture, a branch of humanity that will develop in ways we cannot predict and that will eventually look back at Earth the way that Americans look back at Europe. As the place their ancestors came from, as a home that was left and cannot be returned to, not because it was lost, but because something new was built in its place. The people who go to Mars knowing they may not return are making a wager, not a reckless one, a calculated one. They are wagering that what they do on Mars is worth the cost they may pay, that the science they will produce, the presence they will establish, the foundation they will lay for those who follow, these things are worth more than the certainty of coming home. History suggests they will be right. Every major expansion of the human footprint, across oceans, into mountains, into ice was accomplished by people who accepted that they might not come back. Some of them did not. Their names are often forgotten, but their choices are the reason that the places they went are part of the world we inhabit. The first people on Mars will not be forgotten. Their names will be known. Their choices will be understood. And what they build, however small, however provisional, however fragile, will be the beginning of something that extends far beyond their individual lives, whether they return or not. Let us talk about what we actually know and what we do not know about the question we are examining, because honest science requires distinguishing between established facts, reasonable inferences, and genuine unknowns. And on the question of whether the first people on Mars will return, the ratio of known to unknown is strikingly unfavourable. What we know. We know that the radiation dose accumulated during a round-trip Mars mission of approximately 3 years' duration significantly exceeds current career limits for astronauts. We know that bone loss occurs in reduced gravity environments, and that the rate at 0.38 g is not precisely known, but is almost certainly positive. Bones will be lost. The question is how much. We know that cardiovascular deconditioning occurs in reduced gravity, and that the cardiovascular system of someone who has spent 3 years partly in weightlessness and partly at 0.38 g will be significantly different from what it was at departure. We know that spaceflight-associated neuroocular syndrome affect a large majority of astronauts on long-duration missions, and that some effects persist after return. We know that the return rocket must work on the first attempt, because there is no rescue from Mars. What we do not know. We do not know the long-term physiological effects of 0.38 g specifically. All our data comes from zero gravity or Earth gravity, and the intermediate case is genuinely unexplored. We do not know whether the combination of radiation, reduced gravity, psychological stress, and physiological changes produces effects that cannot be predicted from studying each factor in isolation. The interactions between these stressors are poorly characterized. We do not know whether any specific individual's physiology will deteriorate in ways that make return impossible. This can only be determined for each individual by going and seeing what happens. We do not know whether solar weather during the specific mission dates will include events sufficient to cause acute radiation sickness. This is probabilistic and unknowable in advance. We do not know whether the Mars ascent vehicle will work on the first attempt, because it has never been tested on Mars. We do not know whether the psychological cohesion of a 6-person crew can be maintained over 3 years of extreme isolation, with the communication delay making Earthside support effectively asynchronous. We do not know whether the habitat life support systems will maintain function over 3 years under Martian conditions, because none have ever been operated under those conditions for that duration. What we know we do not know is extensive. What we do not know, we do not know. The unknown unknowns, the failure modes that no one has anticipated because no one has ever done this before, may be more significant still. Every first mission into a genuinely new environment has been surprised by something that the preparations did not anticipate. The first moon landings were surprised by the texture of the lunar surface, the behavior of the dust, the actual thermal environment on the lunar surface. Mars will surprise the first humans there in ways that cannot be predicted from robotic data. This does not mean the mission should not happen. It means the mission should happen with clear eyes about what is known, what is unknown, and what the stakes are. The first people on Mars should be volunteers who understand the genuine probability, Not the optimistic estimate, not the pessimistic estimate, but the honest, best estimate that they may not come home. And they should make their choice with that understanding. They will go. People will choose this. The history of exploration and the evidence from current astronaut selection processes both indicate that there is no shortage of people willing to accept very high personal risk for a sufficiently important goal. The question is not whether the mission will be attempted. The question is whether the people who design it will be honest about what they are asking, and whether those who answer the call, who step onto that spacecraft knowing what they know, will be celebrated for their courage rather than mourned for what they sacrificed. Because the distinction matters. The first people on Mars who do not return are not lost. They are somewhere extraordinary, somewhere human beings had never been before, somewhere that will, if their work succeeds, eventually become home to people who never knew any other world. The courage that takes is real. The cost that courage pays is real. And what that courage makes possible for the people who come after, for the species as a whole, for the long and uncertain future of humanity beyond this planet, is worth knowing clearly before the first boot touches the Martian surface. Let us talk about the specific individuals who are likely to be among the first people on Mars, not as abstractions, but as a category of human being defined by specific psychological and physiological characteristics that the selection process will attempt to identify, and that the mission will test in ways that cannot be fully simulated on Earth. The selection process for early Mars astronauts will be unlike anything that has come before in astronaut selection history. Current NASA and ESA selection processes prioritize technical competence, physiological fitness, psychological stability, and the ability to work effectively in teams under stress. These criteria will remain relevant for Mars selection, but Mars selection will add requirements that existing processes do not explicitly test for. Specifically, the requirement that candidates be psychologically capable of accepting a significant probability of permanent separation from everyone and everything they have ever known. This is not the same as accepting the risk of death. Astronauts have always accepted the risk of death. The ISS has a non-trivial probability of catastrophic failure, and the history of spaceflight includes 18 people who died in training or in flight. Accepting the risk of death is something that can be cognitively processed through frameworks of risk-benefit calculation that humans apply in many high-risk professions. Accepting the probability of never returning home is different in a specific way. Death is an end. Not returning to Earth is not an end. It is a continuation of life in a place that is not home, surrounded by the same small group of people indefinitely, with the knowledge that Earth, everyone you loved, every place you were formed by, every sensory experience that constituted your understanding of normal existence, is permanently out of reach. The people who can accept this and function effectively are not common. They share some characteristics with people who have voluntarily committed to permanent isolation in other contexts: monks in cloistered communities, researchers who have spent multiple years at Antarctic stations, submariners on long patrols. But none of these analogues involves permanent separation from Earth. The Antarctic researcher will eventually return. The submarine will eventually surface. The Mars mission, in the scenarios we have been discussing, may not end with return. Psychological research on people who do well in extreme isolation identifies several consistent characteristics. High levels of what psychologists call psychological flexibility, the ability to accept difficult thoughts and feelings without being controlled by them. a strong sense of meaning and purpose that is tied to the mission rather than to the particular circumstances of their personal life on Earth. The ability to form genuine connection with a small group of people and derive sufficient social sustenance from those connections. Tolerance for monotony and for reduced stimulus variety, without the depression and irritability that affect others in similar conditions. A specific cognitive style that allows them to process threats and uncertainties through problem solving rather than through rumination. These are real, measurable traits. They can be identified through psychological assessment and through simulated missions, Mars analog environments like the Mars Desert Research Station in Utah, or the HI-C's habitat in Hawaii, or the Mars 500 isolation study conducted in Russia, in which 6 people spent 520 days in a sealed facility simulating a Mars mission. These analogues provide useful data, but they are imperfect. The participants always know that the real Mars is not outside the door, that they can exit if they need to, that Earth is accessible. The psychological state of someone who knows that Earth is genuinely inaccessible cannot be fully replicated in simulation. What we do know from simulation studies is sobering. The Mars 500 study, the most comprehensive of these analog missions, found that participants developed increasing sleep disruption over the course of the mission, with some spending more and more time sedentary and socially withdrawn as the mission extended. 3 participants showed signs of significant sedentary behavior and isolation withdrawal that would be concerning in a real mission context. 2 participants maintained high activity levels throughout. The variation between individuals was enormous, suggesting that individual differences in response to long-duration isolation are substantial and that selection matters enormously. The people who thrive in extended isolation tend to be what researchers describe as engaged problem solvers with strong intrinsic motivation. People whose sense of purpose is internally generated rather than dependent on external validation. They are typically not the most socially oriented people. Those who most need human connection tend to struggle most in isolation. Paradoxically, they are also not the most introverted. Extreme introversion can lead to withdrawal from the small group that is available, which undermines the social support that even relatively solitary people need over multi-year timescales. The ideal Mars crew member may be someone who has a deep and genuine scientific or engineering passion for Mars specifically, not just for space exploration generally, but for this planet, this mission, this set of questions. Someone for whom the work itself provides sufficient meaning to sustain motivation through years of difficulty. Someone who forms genuine attachment to a small group and can sustain that attachment through the inevitable conflicts and irritations of close confinement. And someone who has genuinely processed the possibility of not returning in a way that is neither denial nor despair, who has made peace with it in a way that does not require revisiting the question constantly. These people exist. There are people on Earth right now who would thrive on Mars in ways that most people would not. The challenge for selection is finding them, because the characteristics that predict long-duration isolation tolerance are not the same as the characteristics that predict performance in the shorter duration, high-intensity missions that current astronaut selection optimizes for. Let us talk about the specific physiological characteristics that might determine who can return and who cannot. Because if it is true that some people who go to Mars will be unable to return due to physiological changes, the question of who those people will be is not random. There will be predictors, biological characteristics that increase or decrease the probability that a given individual's body will survive the round trip. Age is one of the most significant. Bone loss in reduced gravity is more severe in older individuals whose bones are already beginning the age-related decline in density. An astronaut who is 45 at departure will return at 48 with a bone mineral density corresponding perhaps to someone 55 or 60. An astronaut who is 30 at departure will return at 33 with bone loss on top of a starting density that is substantially higher. The younger astronaut has more physiological reserves. They start from a higher baseline and can lose more before reaching the threshold of clinically significant fragility. But age also affects the ability to tolerate the psychological demands of the mission. Younger people tend to be more psychologically flexible and more able to adapt to novel circumstances. But they also tend to have stronger ties to Earth in the form of parents, siblings, new relationships, potential children who will be born while they are gone. The calculus is not simple. An older astronaut may be more psychologically prepared to accept permanent separation from Earth. They have had more time to form the values and commitments that make such acceptance possible, but physiologically more vulnerable to the irreversible changes of the mission. Sex is another significant variable. Women have consistently shown greater susceptibility to radiation-induced cancer per unit dose than men, a biological reality that drives the lower career radiation limits established for female astronauts. This creates a genuine ethical and practical problem for Mars missions, in which the radiation dose will be large for everyone. It is not that women should not go to Mars. The contributions of female astronauts to any Mars mission would be as important as those of male astronauts. But the radiation risk picture is worse for women, and this needs to be explicitly part of the informed consent process for female crew members. On the other hand, women show lower rates of certain cardiovascular problems associated with spaceflight. The gender differences in physiological response to spaceflight are complex and cannot be summarized as one sex being more or less suited to the mission. The differences are real, distributed across different physiological systems, and require personalized risk assessment for each individual, regardless of sex. Genetics will be increasingly important as genetic profiling becomes more sophisticated. We know that individuals vary substantially in their susceptibility to radiation damage, in their rate of bone loss in response to reduced mechanical loading, in their cardiovascular adaptation to reduced gravity, and in their susceptibility to the optic nerve changes associated with SANS. Some of this variation is genetic. Identifying the genetic variants that protect against the most dangerous physiological changes of a Mars mission, and selecting for or against crew members based on their genetic profile, raises profound ethical questions about genomic discrimination, but also potential life-saving benefits. The ethical questions are real. Is it appropriate to exclude someone from a Mars mission because their genome suggests they are at higher risk of irreversible vision damage? Is it appropriate to include someone because their genome suggests they are unusually radiation resistant? These questions do not have obvious answers. They involve values about autonomy, about fairness, about the obligations of mission designers to crew members and to the success of the mission, that go beyond the science. What is certain is that some people who go to Mars will fare much better than others. The variation in physiological response to the stressors of the mission will be large. Some people will lose relatively little bone and suffer relatively little vision change and maintain robust cardiovascular function and return to Earth in reasonably good health. Others will experience much more severe physiological changes that either make return inadvisable or make recovery from return extremely prolonged and incomplete. Understanding in advance who is likely to be in which category is one of the most important unsolved problems in Mars mission medicine. Let us now talk about the planet itself in more physical detail, about what the Martian environment actually feels like to be in, what the experience of being on Mars would be like at the sensory and perceptual level. Because understanding the first people on Mars requires understanding not just the hazards they face, but the world they face them in. Mars is not uniformly hostile. It is a planet of extraordinary geological variety, ancient terrain covered in impact craters, younger volcanic plains, chasms that dwarf anything on Earth, polar ice caps that advance and retreat with the seasons. It has weather, real weather, with winds, dust devils, clouds, and storms. It has a sky that changes colour through the day, from butterscotch yellow at sunrise and sunset to a more brownish or pinkish hue in the middle of the day when dust is raised into the atmosphere. It has seasons, caused by the same axial tilt mechanism that gives Earth its seasons. The Martian day, the Sol, is 24 hours and 37 minutes. This is close enough to Earth's day that human circadian rhythms will not be dramatically disrupted, one of the few ways in which Mars is physiologically similar to Earth. Astronauts will wake and sleep on a cycle close to their biological norm, something that is not true on the ISS, where the sun rises and sets 16 times per 24 hours. Standing on the Martian surface in a spacesuit, you would see a landscape of extraordinary desolation and extraordinary beauty simultaneously. The rocks would be familiar in shape, the products of geological processes that operate on Mars as they do on Earth, but unfamiliar in colour, stained red and ochre by iron oxide. The sky would be a dusty salmon pink. The horizon would be slightly closer than on Earth. Mars is a smaller planet, and the curvature is more apparent. In the right atmospheric conditions, you might see thin clouds of water ice or CO2 ice at altitude. At night, the stars would be extraordinarily clear. The thin atmosphere provides almost no scattering, and the stars would be as brilliant and as numerous as they appear from the highest and driest locations on Earth. The silence would be profound. Not the comfortable silence of a room or a forest, but the silence of a world where the air is too thin to carry most sounds. The wind on Mars, which can be surprisingly strong during dust storms, barely makes a sound even when it is moving fast enough to raise dust. The thin atmosphere simply does not carry sound efficiently. An astronaut on the Martian surface would hear the sounds produced inside their suit, their own breathing, the sounds of their equipment, communications through their helmet speakers, but the world outside would be nearly silent. This silence is psychologically significant. Human beings are deeply habituated to the ambient sounds of a living world: wind in trees, birds, distant traffic, the background noise that constitutes the acoustic texture of life. The silence of Mars is a different kind of silence from anything experienced on Earth, a silence that is not the absence of sound in a moment, but the absence of the entire category of natural sound that biological environments produce. Astronauts who have experienced this in analog environments describe it as initially striking and eventually deeply unsettling over extended time. The cold would be constant and pervasive. Even in a heated spacesuit, the knowledge that a few centimeters of material stand between you and temperatures that would kill you in minutes shapes the experience of being outdoors on Mars in a specific way. Every EVA carries a constant, low-level awareness of environmental hostility that is qualitatively different from cold weather on Earth. On Earth, cold is uncomfortable, but rarely immediately threatening to life. On Mars, the cold is immediately threatening to life if the spacesuit fails. The dust is another constant. Martian dust is fine, particles of order 1 micrometer in size, and it gets into everything. It accumulates on solar panels, reducing their efficiency. It accumulates on spacesuits and contaminates habitat airlocks. It contains perchlorates, chemical compounds that are toxic to humans at sufficient exposure levels. Managing dust contamination will be one of the unglamorous but critical ongoing tasks of a Mars surface mission. The dust also carries electrostatic charge that makes it cling to surfaces, including visors, making visibility a recurring concern during EVAs. The dust storms deserve particular attention. Global dust storms on Mars, events in which suspended dust covers the entire planet and significantly reduces solar illumination for weeks or months, occur irregularly. The Opportunity rover experienced 2 significant dust storms during its operation, including the 2018 global dust storm that ended its mission by permanently reducing sunlight below the level needed to power the rover's electronics. A crew depending on solar power during a global dust storm would face a critical power emergency. This is another reason that nuclear power is considered essential for human Mars missions. It is immune to dust storm power reduction. The surface of Mars contains fascinating geological record of billions of years of planetary history. The ancient cratered highlands record the period of heavy bombardment that characterized the early solar system. The vast volcanic provinces, Tharsis, a continent-sized dome of volcanic rock, surmounting which stand the 4 largest volcanoes in the solar system, record billions of years of intense volcanism. The Valles Marineris canyon system, longer than the continental United States and in places deeper than the Himalayan peaks are tall, was formed by a combination of tectonic stretching and collapse, erosion, and volcanic processes over billions of years. Most fascinating for the question of life are the ancient lake and river systems. Jezero Crater, the landing site of the Perseverance rover, was a lake approximately 3.5 billion years ago, with a river delta flowing into it from the west and a river channel draining it to the north. The Curiosity rover in Gale Crater has found evidence of a complex lake system with neutral pH water, not acidic, not alkaline, that may have persisted for millions of years. These are the environments where life, if it ever existed on Mars, would have had its best chance. A human geologist in Jezero Crater could examine the delta deposits of the ancient river in a way that Perseverance cannot. A human could climb into the river channel and examine the exposed stratigraphy, the layered record of sediment deposited over millions of years, and select samples with the judgment of a trained geologist responding in real time to what they see. A human could recognize the subtle biosignatures that might indicate ancient life in a way that an automated system may not, because recognizing biosignatures in ancient geological contexts is a skill that depends on experience, pattern recognition, and the ability to follow an unexpected lead wherever it goes. This is what human exploration offers that robotic exploration cannot match. Not raw observational capability. Robots can sense things humans cannot. Not endurance. Robots do not need to sleep or eat or manage their psychology. But judgment, creativity, the ability to see something unexpected and follow it in real time without waiting for Earth to send new instructions that will arrive after the moment has passed. The first humans on Mars will see things that no robotic mission has seen, and will think thoughts that no robotic mission can think. Whether they return or not, what they find will change what we know. Whether that knowledge is worth the cost they pay, the risk they accept, the years they lose, the home they may not see again, is a question that each of them will answer for themselves. Let us talk about what the first decade of human Mars exploration might actually look like. The realistic timeline, the realistic milestones, the realistic setbacks that history suggests will occur even in the best case. Current plans from NASA, SpaceX, and other organizations suggest that the first crewed Mars missions could occur sometime in the 2030s. NASA's Artemis program, which is returning humans to the Moon, is explicitly described as a stepping stone to Mars. SpaceX's Starship, currently under development, is designed as the vehicle that would carry humans to Mars. China has expressed ambitions for crewed Mars exploration in the 2030s to 2040s timeframe. These timelines are almost certainly optimistic. The history of large, complex space programs is a history of delays, cost overruns, and unexpected technical challenges that push launch dates back by years or decades. The Space Shuttle was supposed to launch in 1978 and first launched in 1981. The ISS was supposed to be complete in 2002 and was not completed until 2011. The James Webb Space Telescope was supposed to launch in 2007 and launched in 2021. Mars is harder than any of these, and the timeline compression currently being contemplated by some organizations assumes a pace of development that has no historical precedent in human spaceflight. Assuming something like a 2035 first crewed mission, which would require sustained funding and political commitment at levels not currently guaranteed, the mission would spend the better part of a decade in preparation. Robotic precursor missions would be sent to the target landing site to verify resources, establish communication infrastructure, and pre-position supplies, including the Mars Ascent Vehicle. This is the architecture that makes the first human mission viable, arriving at a site where the most critical systems are already in place and have been tested. The first crew would likely spend their surface time establishing baseline operations, verifying that the pre-positioned systems work as expected, setting up additional habitat modules, beginning systematic geological surveys of the landing site, and learning to work effectively in Martian conditions. The first mission would be primarily an engineering mission, a survival mission, a proof of concept. The science, while important, would be secondary to the task of demonstrating that humans can live and work on Mars. The second mission, if the first succeeds and the political and financial commitment holds, would arrive approximately 26 months after the first, during the next launch window. It might overlap with the return of the first crew, depending on mission architecture, or it might arrive after the first crew has left. It would build on the infrastructure established by the first mission and begin a more systematic scientific program. By the third or fourth mission, perhaps in the early 2040s if the pace is sustained, the presence at the landing site would begin to look less like an expedition camp and more like an outpost. Small-scale food production might be underway. Water extraction systems would be mature and reliable. The habitat would have expanded. The accumulated knowledge of how to work safely and effectively on Mars would be substantial. And somewhere in this progression, in the second or third mission, or possibly earlier, someone will stay when the others leave. Not necessarily because they cannot return, but because the work requires continuity, because they have made a commitment to the place, because the next 26 months feels more important than going home. The first voluntary long-term resident, the first person who chooses Mars. This is how it will happen, not with a dramatic declaration, not with a formal policy decision about who will be left behind, with a choice made by an individual, supported by their crew and by the organizations that sent them, to remain when the option to leave is available. And that choice, whenever it first occurs, will mark the moment that Mars becomes inhabited in the full meaning of the word, not visited, inhabited. What follows from that choice, the people who follow, the generations that grow up there, the society that eventually emerges, cannot be predicted from where we stand now. What can be said is that it will be different from anything that has existed before. A human community on another planet will develop in response to the specific demands and affordances of that planet, its gravity, its resources, its isolation, its extraordinary scientific richness, in ways that no earthbound imagination can fully anticipate. It will also be shaped by the specific people who choose it, who they are, what values they bring, what relationships they form, how they organize their community in the absence of the institutional structures of Earth. All of this will determine what Mars becomes in the first century of human habitation. The founders of any community have disproportionate influence on what it becomes, not because they make formal decisions about its character, but because the culture they establish in the first years tends to persist and propagate even as the community grows. The first Martians, those who choose to stay when they could have left, and eventually those who are born there, will be founders in this deepest sense. They will not know what they are founding. They will be too busy surviving to think about cultural legacy. But what they build in those first years, the informal norms, the technical practices, the relationships between individual and community, will be as foundational to Mars as the choices of the first permanent settlers were to the communities they established on Earth. History rarely gives us the names of those founders. Their individual decisions are obscured by the scale of what comes after. But the first Martians will not be obscured. Their names will be known. Their choices will be documented. The first human to choose Mars over Earth, to say, "I am staying when the ship is leaving," will be one of the most famous decisions in human history. And whether they made that choice because they could not return physically, or because they found something on Mars worth more than the certainty of coming home, or because they simply became someone for whom Mars was more real than Earth, will matter less than the fact that they made it. Let us talk about what happens to Earth during the years of early Mars exploration, because a Mars mission is not only a story about the people who go, it is a story about the civilization that sends them, about the values that sending people to Mars expresses, and about the changes that the knowledge they bring back will create. The first images from a human Mars mission, images of humans walking on a red planet, images of Martian landscapes seen through human eyes, images of the first habitat in the wilderness of another world, will be among the most viewed photographs in human history. The Apollo 11 moon landing was watched by approximately 530 million people, roughly 1/6 of the world's population in 1969, and it transformed the cultural moment in ways that went far beyond the specific achievements of the mission. The first Mars landing will be a larger cultural moment, occurring in a world more connected and more capable of collective experience than the world of 1969. What that moment does to collective human imagination is not predictable. The moon landing inspired a generation of scientists and engineers who went into careers shaped by the sense of possibility it opened. It also produced a cultural moment of unity, the sense that this was humanity doing something, not just Americans or Soviets, that was brief but real. The first Mars landing, if it is executed with the broad international cooperation that the science and the cost suggest it should be, could produce a similar but larger moment. The specific knowledge brought back from Mars will change science in ways that depend entirely on what is found. The discovery of evidence of ancient life, fossilized microbes in ancient lake sediments, complex organic molecules in a pattern consistent with biological origin, isotopic signatures that indicate metabolic activity, would be the single most transformative scientific discovery in human history. It would answer the question of whether life is a cosmic phenomenon or a local accident. It would transform biology, philosophy, religion, and our understanding of our own place in the universe. The non-discovery of evidence of life, the demonstration that Mars, despite its favourable early conditions, never generated life, would be equally significant in a more troubling direction. It would suggest that the origin of life is harder than the conditions approach implies, that there is a filter between chemistry and biology that is more difficult to cross than we thought, that the galaxy may be far emptier of life than the optimistic estimates suggest. Both discoveries, life and no life, change everything. They just change different things. The human experience of Mars, the knowledge gained not through instruments but through perception and judgment, and the kind of understanding that comes from being in a place rather than sending a machine to be there, will come back with the people who return, and will reshape our understanding of the solar system in ways we cannot fully anticipate. Every major expedition in history has returned with knowledge that changed the world of ideas in ways that the expedition planners did not predict. The Mars expedition will be no different. What the people who do not return will bring back is something different. They will not bring back their knowledge in person, but they will transmit it through the data they collect, through the communications they send, through the record of their work that will be preserved and studied for generations. The first people on Mars who stay will contribute to science for as long as they live on Mars. Their contributions will be different from those of people who return. They will be made by people who have chosen a specific place and a specific set of questions that can only be answered from that place. There is a kind of scientific devotion in this that has parallels in the history of scholarship. Scholars who devoted their lives to a single question. Scientists who spent decades in a single location learning everything that could be learned there. Monks who preserved and transmitted knowledge across centuries in cloistered communities. The first permanent residents of Mars will be this kind of person, deeply committed to a specific project, located in a specific place, willing to spend their life in service of understanding something that can only be understood by being there. The science they produce will be extraordinary. The life they live will be extraordinary. And whether that life includes a return to Earth, whether it ends at the place it was lived or on the world that launched it, it will be one of the most significant lives any human being has ever lived. The first people on Mars, the first people who may not return, the first Martians. They are almost certainly alive right now, somewhere on Earth, training or studying or dreaming, not yet knowing that they will be the ones who go. Their names are not yet famous, their choices have not yet been made, but the world they will change, both the one they leave and the one they find, is already waiting for them. Let us talk about the children, because the question of whether the first people on Mars will return cannot be fully examined without confronting the question of what happens when people on Mars have children, and what those children's existence means for the question of return more broadly. The biology of human reproduction in Martian conditions is almost completely unknown. We have no data on whether human conception is possible at 0.38 g. We have no data on whether a human embryo can develop normally in Martian gravity. We have no data on whether a human fetus carried to term in a Martian habitat will be healthy. We have no data on the effect of chronic low-level radiation exposure, at the levels present on the Martian surface even inside a habitat, on the developing human organism across the full 9 months of gestation. On Earth, the developing organism is protected from radiation by the mother's body and by the shielding provided by Earth's magnetic field and atmosphere. On Mars, the mother's body provides the same shielding as on Earth, but the background radiation penetrating the habitat walls and reaching the developing fetus is substantially higher. Radiation is a known teratogen. It causes developmental abnormalities at sufficient doses. The specific doses involved in a Martian habitat are within a range where the risk of developmental effects on a fetus is genuinely uncertain. This uncertainty is not merely academic. If people are going to live on Mars indefinitely, if the vision of a permanent human presence is to become reality, they will eventually have children there. The question is not whether this will be attempted, but under what conditions and with what knowledge. The most conservative approach would be to prohibit reproduction during early missions until enough is known to make a reasonable assessment of the risks. The most aggressive approach would be to allow natural reproduction and learn from what happens, which is the approach that characterized early human expansion into new environments throughout history, with consequences that ranged from tragic to transformative. The medical ethics of this question are genuinely difficult. An embryo or fetus cannot consent to being born in conditions that may harm its development. The parents cannot make an informed decision about a risk that has never been studied. Mission planners cannot establish safety thresholds for something that has no data. And yet, preventing reproduction indefinitely for all crew members in a Mars settlement is also ethically problematic. It places constraints on fundamental human choices that are difficult to justify except as temporary emergency measures. The physics of the problem suggests that children born on Mars will be fundamentally different from children born on Earth, not in their genetics, which will be fully human, but in their physiological development. A child who grows and develops in 0.38 g will develop a skeletal system calibrated to that gravitational loading. Their bones will form with the density and geometry appropriate for a world where things weigh less than 2/5 of what they weigh on Earth. Their cardiovascular system will develop for the demands of pumping blood against 0.38 g. Their proprioceptive system, the body's sense of its own position and movement, will calibrate to a gravitational environment fundamentally different from Earth's. This child will be Martian in a physiological sense that their parents are not. Their parents arrived on Mars as fully formed adult organisms, whose bodies were shaped by Earth and then adapted, partially and imperfectly, to Mars. The Martian-born child will be shaped by Mars from the beginning. They will be as well adapted to Mars as any human being can be, and they will be correspondingly less adapted to Earth. What happens when a Martian-born child attempts to visit Earth? Or what happens to the physiology of a Martian-born person who attempts to live on Earth permanently is a question we cannot answer from existing data. But we can make inferences. A cardiovascular system that developed pumping blood against 0.38 g will be underpowered for Earth's 1 g. A skeletal system that developed under 0.38 g loading may be too lightly constructed to handle Earth's loading without fracture risk. The proprioceptive system will have calibrated to a world that feels substantially different from Earth in every movement and interaction. The Martian-born person attempting to live on Earth might find it physiologically comparable to an Earth-born person attempting to live with a significantly elevated gravitational field, perhaps 2.6 times what they evolved for. This is not immediately fatal. Humans can function under elevated gravitational loading, as demonstrated by fighter pilots who experience several Gs during maneuvers. But living at 2.6 G continuously for years would be chronically debilitating. The cardiovascular demands would be enormous. The skeletal loading would be punishing. The fatigue would be constant. This means that the children born on Mars, if they grow up there, if their bodies develop fully in Martian conditions, may be physiologically unable to live on Earth, even if they want to. The question of return that we have been examining throughout this exploration applies to the first generation as a matter of risk and choice. For the second generation, the Martian-born, it may apply as a matter of biology. They will be Martian not just by birth and experience, but by the physical structure of their bodies. This is a profound threshold in human history, the moment when a human being is born who cannot live on the planet from which their species originated. Not because of illness or injury, but because they are adapted to a different world. Not Earth's children who happen to be on Mars, Mars's children who happen to be descended from Earth. The species divergence this represents is not genetic. A Martian-born person has the same genetic code as their Earth-descended parents. But evolutionary biology recognizes that populations separated by environment and with different selective pressures can diverge physiologically over relatively short timescales, even without genetic divergence. The developing human body is extraordinarily plastic. Its physical form is shaped powerfully by the environment in which it grows. The Martian environment will shape human bodies differently from the Earth environment. Over generations, this divergence will accumulate. Whether this constitutes the beginning of speciation, the process by which one species becomes two, is a question for the biologists of future centuries rather than for us. What we can say is that the first generation of Martian-born humans will be different enough from Earth-born humans in their physiological adaptation that the practical barriers to living on Earth will be substantial. And with each subsequent generation born and raised on Mars, those differences will compound. The implication for the question of return is stark. The question we started with, will the first people on Mars return to Earth, has a time horizon beyond which it becomes irrelevant. The question applies to the first generation. For the second generation, it becomes a question of whether they can visit Earth, not whether they can live there. For the third generation, it may become a question of whether they can survive on Earth at all under their own physiological resources. The biological Rubicon may be crossed within a century of the first human landing. This is not a prediction of catastrophe. It is a prediction of transformation. The branching of the human lineage into multiple planetary populations is, from the perspective of deep time, an extraordinary development in the history of life on this planet. From the perspective of individual human lives, of parents watching children born on another world, of children who have never seen Earth's blue sky, it is something more personal and more immediate. Let us talk about what it means for the species as a whole. Because we have been examining the question of return primarily from the perspective of the individual, the specific person who goes to Mars and may not come back, but the question has a larger dimension that is worth examining. Humanity's expansion onto Mars would be the first time in the 300,000-year history of our species that we have established a presence on a second world. Every previous expansion, across continents, across oceans, to the poles and the highest mountains, has been expansion within the same planetary system. The same atmosphere, the same sky, the same gravity, the same sun. Mars is different in every one of these respects, and similar in almost none. The expansion to Mars, therefore, represents something genuinely new in human history, not a larger or faster version of what came before, but a qualitative change in the relationship between humanity and the universe it inhabits. We have been a single-planet species for our entire existence. We will become a multi-planet species for the first time. The individuals who make this transition possible, who go and who stay, and who build the first fragile foothold on another world, are doing something that has no precedent. History provides analogies, but not equivalents. The settlement of the Pacific Islands by Polynesian navigators, who crossed thousands of kilometers of open ocean in outrigger canoes with no charts and no certainty of finding land, is often cited as the most comparable human exploration feat. The Polynesian navigators accepted the real possibility of death by drowning or starvation in an empty ocean in search of new land. Some of them found it, some of them did not return. But the Polynesian navigators, remarkable as they were, remained on the same planet. They remained under the same sky. They found land that could support the same biology, the same agriculture, the same fundamental way of being human. Mars offers none of these continuities. The differences are not of degree, but of kind. This matters because it means that the people who go to Mars, and especially those who stay, are not pioneers in the traditional sense of people who find new land suitable for human habitation. They are pioneers in the deeper sense of people who create the conditions under which human habitation becomes possible, who build the technology, establish the knowledge, develop the practices, and pay the cost that makes it possible for those who follow to live there. The first settlements were not habitable when the settlers arrived. They became habitable through the settlers' work. Mars is not habitable for humans when the first crew arrives. It will become more habitable, never fully habitable in the Earth sense, through the work of the people who go there, and through the technology they develop and the infrastructure they build. The first people on Mars are not finding a new home. They are building one, at enormous personal cost, under conditions of extreme hardship, with no certainty that what they build will last. The history of human settlement is full of settlements that did not last, failed colonies, abandoned outposts, places where people went and died without establishing anything that survived them. The Norse settlement of Vinland, North America, lasted approximately a decade before being abandoned. The Roanoke colony in Virginia disappeared entirely with no confirmed trace of its inhabitants. There were settlements on the margins of the habitable world that simply could not sustain themselves and were given up. Mars could be the greatest failed settlement in human history if the political will and financial commitment to support early missions does not hold across the decades required for a permanent presence to become self-sustaining. The first crew lands. The second crew arrives. The third mission is cancelled due to cost overruns or political change or a competing priority. The crew on Mars, 3 or 4 people, runs low on critical consumables. A return mission is mounted on emergency timelines. Mars is abandoned. The foothold is lost. This is not a fanciful scenario. It is the scenario that occurred with the Moon. where 6 successful landings over 3 years were followed by 50 years of no human presence, because the political and financial commitment that sustained Apollo could not be maintained indefinitely. If the same pattern repeats with Mars, if early successful missions are followed by program cancellation before a permanent presence is established, then the first people on Mars may be remembered not as the founders of a new world, but as the participants in a mission that proved it was possible to go, and then failed to prove it was possible to stay. Preventing this requires something that no single mission can provide: sustained institutional and political commitment across multiple decades and multiple governments and multiple funding cycles. The United States government that funds the first Mars mission may not be the government that funds the fifth. The technology company that builds the first Mars rocket may not be the company that sustains the 20th mission. The cultural moment that makes Mars funding politically viable in the 2030s may have passed by the 2050s, when the permanent presence requires the most sustained support. This is the fundamental challenge of Mars that goes beyond the engineering and the medicine and the psychology. Mars requires a commitment on a timescale that is longer than political cycles, longer than corporate planning horizons, longer than individual human careers. It requires the kind of multi-generational commitment that built the great cathedrals of medieval Europe. Projects begun by people who knew they would not live to see them finished, continued by people who had never met the founders, completed by people for whom the founders were history. Whether the civilization of the early 21st century is capable of that kind of commitment is not a question that can be answered by examining the physics of Mars or the physiology of astronauts. It is a question about human values and human institutions and human capacity for sustained purpose. It is a question about whether we are the kind of species that can commit to something larger than any individual or any generation, and then actually follow through. Let us talk about what space agencies and private companies are actually planning right now, because the question of whether the first people on Mars will return is not purely theoretical. It is a question with specific institutions behind it, specific timelines being worked toward, specific vehicles under development, and specific decisions being made by real people in real organizations. NASA's current planning for human Mars exploration is organized around the Moon to Mars framework. The Artemis program, which aims to return humans to the Moon and establish a sustainable lunar presence, is explicitly conceived as a proving ground for the technologies, operations, and systems that will eventually be needed for Mars. The Gateway, a small space station in lunar orbit, would serve as a staging point for missions to the lunar surface, and would eventually support missions departing for Mars. The Artemis program is currently funded and actively underway, with Artemis 3 planned to land humans on the Moon in the mid-2020s. NASA's planning documents describe a phased approach to Mars, with notional missions beginning in the late 2030s or 2040s. The specific mission architecture, what vehicles would be used, what the mission duration would be, what the crew size would be, has not been finalized and will depend on the outcomes of Artemis missions and the development of deep space propulsion technology. NASA's current planning does not commit to a specific Mars landing date and acknowledges that the timeline is dependent on sustained funding at levels not currently guaranteed. SpaceX's planning is more aggressive in timeline and more definite in architecture. Elon Musk has publicly stated targets for the first uncrewed Starship mission to Mars in 2026 and the first crewed mission potentially in 2028 or 2029. targets that virtually all independent observers consider extremely optimistic, given the current state of Starship development and the regulatory and testing requirements that must be met before a crewed deep space mission could be approved. More realistic timelines from SpaceX's own internal planning suggest the early 2030s at the earliest for a crewed Mars mission. What SpaceX offers that no other organization currently offers is a vehicle architecture that could in principle support the payload mass requirements of a human Mars mission. Starship, the fully reusable stainless steel launch vehicle currently undergoing development and testing, is designed to carry approximately 100 metric tons to low Earth orbit and to be refueled in orbit for deep space missions. This payload capacity is roughly what would be needed to send a meaningful quantity of supplies and habitat to Mars, along with a crew. The Starship development program has experienced multiple dramatic failures, followed by eventual successes, a pattern consistent with SpaceX's testing philosophy of rapid iteration rather than exhaustive pre-launch verification. The vehicle will need to demonstrate reliable performance in Earth orbit, reliable orbital refueling, and reliable deep space navigation before it could responsibly carry humans to Mars. None of these capabilities have yet been demonstrated. The development timeline is uncertain. China's National Space Administration has published aspirational goals for crewed Mars exploration in the 2030s to 2040s timeframe. China has demonstrated substantial competence in lunar exploration. The Chang'e program has successfully landed on the Moon multiple times, including the far side, and is developing the Long March 9 heavy lift rocket that would be needed for deep space missions. Whether China's stated Mars ambitions will be backed by the sustained funding and political commitment required is not externally verifiable. The European Space Agency, Japan's JAXA, and other national space agencies are primarily engaged in robotic Mars exploration and in supporting roles for larger international human Mars programs, rather than developing independent crewed Mars capability. The ExoMars program, a joint ESA-Roscosmos mission that has been troubled by the disruption of European-Russian space cooperation following the 2022 invasion of Ukraine, represents one of the more significant current investments in Mars science, though it is robotic rather than crewed. The economic model for Mars exploration is in flux. The Apollo program was funded entirely by the US government at a cost of approximately $25 billion in 1969 dollars, equivalent to perhaps $200 billion today, over approximately a decade. This level of government spending for a single space program is unlikely to be replicated. The commercial model pioneered by SpaceX, in which private investment supplements government contracts and the vehicle is designed for commercial reuse rather than single mission use, offers a potential path to lower-cost Mars exploration. But commercial space has historically been good at reducing the cost of access to low Earth orbit and has not yet demonstrated the capability to mount deep space human missions. The financing of the first human Mars mission remains one of the most uncertain aspects of the enterprise. The mission will be expensive. Estimates range from $100 billion to over $1 trillion, depending on architecture and timeline. And the political and economic sustainability of that expenditure across the 15 to 20 years of development that precede a first mission is genuinely uncertain. Space programs have been cancelled before. Constellation, NASA's previous program to return to the Moon and eventually go to Mars, was cancelled in 2010 after 6 years and approximately $9 billion of spending. The lesson of Constellation, that program cancellation is a real risk even for high-profile programs, has not been forgotten by those who plan for Mars. Let us talk about what the return actually looks like as an engineering problem, because we have discussed the physiological challenges of return and the orbital mechanics constraints, but have not fully examined what the physical act of returning from Mars requires in engineering terms. The return mission requires several distinct components that must all work. First, the Mars Ascent Vehicle, a rocket that launches the crew from the Martian surface into Martian orbit. The MAV must be light enough to have been transported to Mars in the first place, must have survived storage on the Martian surface during the crew's stay, and must work perfectly the first time because there is no rescue if it fails. The MAV is one of the most technically challenging components of any Mars mission architecture, because it must be pre-positioned on Mars before the crew arrives, sent ahead on an earlier mission, and must remain functional in the Martian environment for potentially years before it is needed. The Martian environment is challenging for stored hardware. Temperature cycles that can range from -60 to +20 degrees Celsius daily. Dust that penetrates every possible gap. Ultraviolet radiation that degrades polymer materials. And perchlorate chemistry that can corrode certain metals. Every system on the MAV must be designed to survive these conditions for years and then perform flawlessly. NASA's concept for the MAV involves launching it from Mars on liquid oxygen and liquid hydrogen propellants that would be produced on Mars from the Martian atmosphere and subsurface water, another application of in situ resource utilization. This reduces the mass that must be transported from Earth. Propellant is heavy, and if it can be made on Mars, the MAV itself can be launched from Earth without the propellant, saving enormous mass. But this requires that the propellant production systems work reliably in Martian conditions, adding another layer of systems that must not fail. Once in Martian orbit, the crew must rendezvous with the Earth return vehicle, the spacecraft that will carry them home. The ERV must have been pre-positioned in Martian orbit or must arrive from Earth on schedule to meet the crew. The rendezvous and docking in Martian orbit, with the communication delay to Earth preventing real-time mission control support, must be executed autonomously by the crew with confidence and precision, because a failed rendezvous leaves the crew in Martian orbit with no alternatives. The transit from Mars to Earth takes 8 to 9 months. The vehicle must sustain the crew in adequate health across this transit, managing the physiological challenges we have discussed, maintaining life support, providing sufficient food and water, and medical capability. The communication delay during part of this transit will be as large as 44 minutes round trip, nearly as bad as on the Martian surface, requiring the same autonomous operation capability. Earth entry and landing is perhaps the most dangerous moment of the return, the highest G event the crew will experience after years in reduced gravity. The thermal protection system of the vehicle must survive the extreme heat of atmospheric re-entry. The deceleration systems, whether parachutes, retro-rockets or some combination, must function to bring the crew to a safe landing. And the crew itself must survive the physiological stress of deceleration after years of deconditioning. This is the sequence that the phrase, "the first people on Mars may not return," compresses into a single phrase. Each step in this sequence has a probability of success less than 1. The combined probability of all steps succeeding, the mission succeeding end to end, is the product of those individual probabilities. For a first mission attempting an end-to-end capability that has never been demonstrated, the combined probability of complete success is genuinely uncertain and may be lower than mission planners are comfortable acknowledging publicly. What mission planners can do is design for graceful degradation, systems that fail in ways that preserve as many options as possible rather than failing catastrophically. If the MAV underperforms and achieves a lower than planned orbit, can the crew nonetheless rendezvous with the ERV if the ERV adjusts its orbit? If the ERV propulsion system has reduced performance, can the crew still reach Earth on a longer trajectory? If the landing system has a partial failure, can the crew still survive an impact at higher than planned velocity? These are the questions that drive Mars mission architecture design. Every component is designed with backup systems and contingency modes. Every sequence is planned with alternatives. The goal is not to achieve perfection, which is not achievable, but to ensure that no single failure is catastrophic, that every failure provides options rather than ending options. But there is a limit to graceful degradation. Some failures on a Mars mission are unrecoverable by definition. A MAV that does not ignite leaves the crew on the Martian surface permanently unless another MAV can be delivered, which would take 26 months minimum and requires that another mission was already in preparation. A crew that cannot survive the physiological stress of Earth re-entry cannot be brought home by adjusting the engineering of the system. A crew member who requires urgent medical intervention beyond the capability of the mission's medical resources cannot be given that intervention. These unrecoverable failures are the ones that make the question of whether the first people on Mars will return genuinely uncertain. Not uncertain in a technical sense that more analysis could resolve. Uncertain in an irreducible sense that depends on how specific events unfold, how the specific people respond to specific conditions over specific months and years, in ways that cannot be predicted from pre-mission analysis. This irreducible uncertainty is the honest answer to the question. We do not know whether the first people on Mars will return. We can say that with sufficient engineering investment and careful mission design and a degree of good fortune, they can return. We can say that without sufficient investment and without care and with poor luck, they cannot. And we can say that the decision to go anyway, knowing this, is the most courageous thing any human being in our time could choose. The first people on Mars who do not return will not have failed. They will have gone. And going, with full knowledge of what it costs, is a form of courage that history recognizes in its finest moments. The people who return will have accomplished something that changes the definition of what humanity is. A species that has visited and survived another planet and come home to tell the story. The people who do not return will have accomplished something that changes the definition of what humanity can become. A species that inhabits more than one world. Both things are worth doing. Both require courage that most people will never be asked for, and that the people who are asked for it will find in themselves, perhaps to their own surprise. We are sending people to Mars in the lifetime of people alive today. They will go knowing what they risk. Some of them will come back. Some of them may not. And what they do there, what they find, what they build, what they learn, what they lose, will change the world they left and begin the world they arrive in. That is the actual situation, not the inspiring version that leaves out the risk, not the pessimistic version that dwells only on the danger. The honest version, in which courage and risk and knowledge and loss and discovery are all present simultaneously, because that is what genuine exploration has always looked like. There is a moment that will happen, not hypothetically, actually, specifically, a moment that will occur in the lifetime of people alive today, perhaps within the next 2 decades, perhaps within 3, but within a time frame that is not geological or astronomical, but human, a moment measured in years, not millions of years. A person will board a spacecraft. They will know the radiation numbers. They will know the bone loss projections. They will know the communication delay, the return rocket logistics, the dust storm risk, the psychological isolation data from every analog study ever conducted. They will have read everything written about what they are about to do. They will have spent years training for it, and they will board the spacecraft anyway. The door will close, the engines will fire, and they will leave. This is not a metaphor. This is a specific future event, as certain as any future event can be, because the physics makes it possible, and the human impulse to go somewhere new when the technology allows it has never yet failed to be expressed. Someone will go to Mars. The only uncertainty is when. What is genuinely uncertain, what cannot be determined until the mission actually happens, is whether everyone who goes will come back. And this uncertainty is not the kind that more analysis or more testing will resolve. It is the kind that can only be resolved by the going itself, by the specific interaction of specific bodies with specific conditions over specific years in a specific place that has never had humans in it before. Some of the people who go will come back. This is the most likely outcome for a well-designed and well-supported mission. They will land on Earth after years away, unable to walk unaided, requiring months of rehabilitation, carrying radiation doses that will follow them in health statistics for the rest of their lives. They will be changed in ways that cannot be fully predicted or measured until after the change has happened. And they will be the first human beings who have been to Mars and returned. The first people for whom the question has a completed answer. What they will have seen: dust plains stretching to a horizon slightly closer than Earth's. A sky that is salmon and butterscotch at the edges and deeper russet overhead. Stars that rise without twinkling through air too thin to scatter their light. A sun that is smaller and dimmer than from Earth, but still bright enough to cast hard shadows on red rocks. Silence so complete that the sound of their own breathing is the loudest thing in the world. They will have held Martian soil in their gloves and examined it for what it contains, and may have found something in it that changes what we know about whether life is a phenomenon of one world or of many. They will have looked at ancient lake beds and river channels and asked the oldest question that can be asked in that specific place: was there ever anything alive here? And they will have come closer to answering that question than any human being before them, and perhaps closer than any robotic mission could have come, because they were there with a trained mind and the ability to follow the unexpected wherever it led. They will have looked at Earth from Mars, from 100 million kilometers away on average, sometimes closer, sometimes farther. A bright blue dot, brighter than any other star, but still a dot. The dot that contains everyone they love, everyone they know, everything that constitutes their history and their context. The dot that they left and that they are going back to. And they will have understood, at a level that no simulation, no photograph, no intellectual exercise could produce, what it means to be away from home, what home actually is, what it costs to leave it, and what it means to return. Some of the people who go will not come back. Whether this means some of them will die on Mars, or some of them will survive on Mars but be unable to return due to physiological changes, or some of them will choose not to return because what they find there makes staying the more meaningful choice. The specific mechanism is less important than the fact itself. The first Mars missions will not achieve a 100% return rate. This is not pessimism. It is the honest assessment of what we know about the risks and what we know about the complexity of the enterprise. The people who do not return will not disappear from human consciousness. They will transmit. Every day that they survive on Mars, they will send data, images, scientific reports, personal messages, observations that no one has made before. They will do science and engineering, and perhaps art. They will develop a relationship with a specific landscape on a specific planet that no human being has ever had before. The deep familiarity of daily life in a place. The knowledge that comes from having been somewhere through many seasons and many conditions. And eventually, their transmissions will stop, either because they have died or because something has failed beyond the capacity to fix it. The last message will arrive on Earth after its 10 to 20 minute journey across the solar system. It will be received and archived. And the people on Earth who receive it will know that they are hearing the last words of someone who lived and worked and perhaps flourished on another planet for a time and then was gone. This will be a grief unlike any other grief in human history. Not the grief of someone lost at sea or on a mountain, someone lost in Earth's own environment. The grief of someone lost in another world entirely. Someone who went so far that even the grief cannot fully follow. The distance between Mars and Earth is great enough that the news of a death takes 10 to 20 minutes to arrive. And in that gap, in that interval between the moment something happens and the moment anyone on Earth knows it happened, there is a loneliness that no other human loss has contained. The people who made that choice, who went knowing the risk, who built what they built and found what they found, and stayed until they could not stay any more, will be mourned. But they will also be something else that grief does not fully contain. They will be the first of something, the first of a line that will eventually, if the project succeeds, if the commitment holds, if the technology advances, populate a second world. They will be the founders in the deepest sense. The people whose willingness to go and not necessarily return made it possible for those who came after to go with greater confidence and greater capability, and eventually to stay, not because they had no choice, but because Mars had become home. The question we started with, will the first people on Mars return to Earth, is in the end not the most important question. It is a question about individuals, about specific people and specific outcomes. The more important question is what the going accomplishes, what it makes possible, what it changes. And what it changes is everything. It changes what we know about Mars, about whether life is unique to Earth, about the geology and chemistry and history of a world that has been studied from a distance and that will finally be studied from within. It changes what we can do, because the engineering and operational knowledge gained from the first missions makes the second missions more capable, and the second makes the third more capable, in a progression that has characterized every major expansion of human presence into new environments. It changes who we are, because a species that has reached another planet and sustained a presence there is not the same species it was before, even if nothing else about it changes. The first people on Mars will change what humanity is, whether they return or not. They are alive somewhere on Earth right now. Unknown, unpredictable in their future. Training, perhaps, studying, working in laboratories or design offices or simulators, developing the skills and knowledge that will eventually qualify them for a mission that may still be a decade or two away. They do not yet know, cannot yet know, that they will be the ones who go. That their name will be spoken in the same breath as the names that defined what their species was capable of. Some of them will come home. They will step off the spacecraft and step onto Earth and stand, shakily, with assistance, having to relearn what weight feels like, on the ground of the planet that made them. And they will have seen Mars. They will know what it is like to stand there, and that knowledge will be in them forever, unreproducible, unrepeatable, belonging to a very small number of people who will carry it for the rest of their lives. Some of them will not come home. They will be on Mars, working for as long as they can work, seeing what they see, sending what they can send, living in a habitat on a red planet under an alien sky. And when they are gone, when the transmissions stop, they will be the first humans ever to rest in Martian soil. Their graves, if they have graves, will be the most distant graves in human history, the most isolated. The most permanent, because Mars has no erosion in the way Earth does, no oceans to submerge and reclaim, no active geology to transform the surface on timescales of thousands of years. A grave on Mars will remain a grave essentially unchanged for longer than human civilization has existed. The planet will hold them carefully. Its dry, cold chemistry, its thin, cold air, its absolute silence. It will preserve them in the way it preserves everything, without care, without malice, simply because the conditions there are preservation conditions. They will be there for a long time, long after everyone who knew them is gone. Long after the specific missions that brought them there are history. Long after Mars itself has been transformed by human presence, if it is ever transformed, their resting place will be somewhere on that planet. And perhaps someone will find it one day, someone who knows what it is and what it means. Someone for whom Mars is home in the deepest sense, the place they were born, the place they have always known. And they will stand at that marker and understand what it cost to make their world possible. You are alive now. Mars is waiting. The first people who will go there are alive now too. The question of whether they will return, the question we have been sitting with throughout this, will be answered in our lifetimes. Not by us, by them, by the specific people who board the specific spacecraft, who do the specific work, who find the specific things, who make the specific choice when the window opens and the question becomes real. We will watch, we will hope, we will grieve, and we will celebrate. And however it ends for each of them, home or not home, Earth or Mars, return or permanence, what they do will be the most significant thing any human beings have done since the first humans looked at a horizon and decided to walk toward it. They will go. Some will return. Some may not. And that distinction, as profound as it is, will matter less than the fact of the going itself. We are a species that goes, even when we do not know if we will come back.